This is module 4 of chapter 2. In this module, we shall discuss two other interpolation methods called Aitken interpolation method and other is called Hermite interpolation method. The Aitken interpolation method is based on iteration. In this method, a lot of polynomials, the interpolating polynomials are generated, and using these interpolating polynomials, finally we construct the polynomial of degree n. So, this method, that means the Aitken interpolation method, is a iteration method and it is used to find the higher order polynomial by using the lower order polynomials. Now, we describe Aitken interpolation method. At first step, linear polynomials between 2 points x 0 y 0 and x j y j for j equal to 1 to n are determined. That means, n linear polynomial are constructed at the first step, and these are called the first approximation of Aitken interpolation method. In second step, we construct a quadratic polynomial, a set of quadratic polynomials for the point x 0 y 0, x 1 y 1 and x j y j, where j equal to 2 to n. The second approximation be performed with the help of first approximation, and this actually reduces the computation effort, and this process is repeated for n times. In details, let the linear polynomial for the points x 0 and y 0 and x 1 y 1 be denoted by p 0 1 x. That means that this particular polynomial is denoted by p 0 1 x, and it is given by p 0 1 x equal to x minus x 1 by x 0 minus x 1 into y 0 plus x minus x 0 divided by x minus x 0 into y 1, and this polynomial is obtained from linear Lagrange interpolation formula, and after rearranging this expression becomes 1 by x 1 minus x 0 whole into x 1 minus x into y 0 minus x 0 minus x whole into y 1 equal to 1 by x 1 minus x 0, and the terms within bracket can be expressed in terms of a determinant of order 2. The first row contains y 0 and x 0 minus x, and second row contains y 1 and x 1 minus x. So, this is the first polynomial p 0 1 x. Similarly, for the points x 0 y 0 and x j y j, the linear polynomial is denoted by p 0 j and it is equal to 1 by x j minus x 0 into a determinant of order 2. The first column contains the value of y, that means y 0 y j, and second column contains x 0 minus x and x j minus x, and this is true for all j equal to 1 to n. That means, a set of n linear polynomial are constructed in the first stage. In second iteration, we consider 3 points. One is x 0 y 0, second one is x 1 y 1, these 2 points are fixed, and the third point is x j y j, where j equal to 2 to n. This polynomial be denoted by p 0 1 j x, and it is obtained as p 0 1 j x equal to 1 by x j minus x 1 into a determinant of order 2. The first column contains p 0 1 x and p 0 j x, and second column contains x 1 minus x and x j minus x, where j equal to 2 to n. That means, all the quadratic polynomials are obtained with the help of linear polynomials which are available in first step. In general, for k plus 2 points x 0 x y 0, x 1 y 1 up to x k y k and x j y j, that means the first k plus 1 points are fixed and the last point x j y j is variable. So, for this k plus 2 points, we obtain the k plus 1 degree polynomial, which is given by p 0 1 2 up to k j x equal to 1 by x j minus x k into a determinant of order 2. The first column contains a polynomial of degree k, that one is denoted by p 0 1 2 k x, and another polynomial of degree k, and that one is p 0 1 2 up to k minus 1 j x, and second column contain x k minus x and x j minus x, and this is true for all j equal to k plus 1 to n. So, the entire calculation can be represented as a tabular form shown below, and this table helps us to calculate the interpolating value for a particular problem. In this table, the first column represents the arguments and second column contains the value of ordinates, that means the value of y. Third column contains n linear polynomials, fourth column contains n minus 1 quadratic polynomial, and next column contains n minus 2 cubic polynomial, and so on. And the last column represents the difference between the arguments and the values of x, that means x 0 minus x, x 1 minus x, and lastly x n minus x. Now, let us consider one example to explain this method. So, for this given table of values x and y x, we have to determine the value of y when x equal to 1.5 using Aitken iteration interpolating method. So, in this case x equal to 1.5, that one given. Now, we calculate the first approximation, that means we calculate or generate the polynomial of degree 1 for j equal to 1, 2 and 3, because the number of points is 4 is given in this problem. The formula is p 0 j equal to 1 by x j minus x 0 into a determinant of order 2. The first column contains y 0 y j, second column contains x 0 minus x and x j minus x. When j equal to 1, then p 0 1 equal to 1 by 1, because x j minus x 0 is 1, and the value of y 0 and y j are substituted, and the value of x 0 minus x is minus 1.5, and that one for x j minus x is minus 0.5. So, after calculating this determinant, the value of p 0 1 is equal to 30.55. Similarly, the value of the polynomial p 0 2 is equal to 29.8, and similarly the value of the third polynomial p 0 3 equal to 30.85. Now, using this value, the updated table becomes this one. The first column contains the arguments, second column contains the ordinates, and first column contains the values of the linear polynomial which are calculated in first stage. The second approximation are determined as follows. The formula is p 0 1 j equal to 1 by x j minus x 1. First column contains two polynomial of degree 1, that are p 0 1 and p 0 j. Second column contains x 1 minus x and x j minus x, and this formula is valid for j equal to 2 to 3. That means, this formula generates two quadratic interpolating polynomial. For j equal to 2, the value of p 0 1 2 equal to 1 by 1, here x 2 minus x 1 is 1, and note that the first column of this determinant is 30.55 and 29.80. These values are obtained in first stage, and the second column represents the value of x 1 minus x, that one is minus 0.5, and second value is 0.5, that one is the value of x 2 minus x. So, after simplification, the value of p 0 1 2 equal to 30.175, and when j equal to 3, the value of p 0 1 3, that means the second quadratic polynomial, is equal to 1 by 2, because x 3 minus x 1 is equal to 2, and p 0 1 equal to 30.55, but p 0 3 is 30.85, and the values of x 1 minus x is remains unchanged, that one minus 0.5, and x 3 minus x, this is equal to 1.5. So, after simplification, this becomes 30.625. So, after second approximation, the updated table is this one, that means the fourth column is updated with the previous table. That means, fourth table is added, that values are 30.175 and 30.625. Now, using these values, that means quadratic polynomial, we determine the third approximate values of the polynomial p 0 1 2 j, but in this case j is only 1, that one is 3, and the formula is 1 by x j minus x 2, and the determinant of order 2, the first row of this determinant is p 0 1 2 and x 2 minus x, and second row is p 0 1 j xj minus x. So, for j equal to 3, this formula becomes p 0 1 2 3 equal to 1 by 1, because the value of x3 minus x2 is 1 and the value of p 0 1 2 is 30.175 and value of p 0 1 3 is equal to 30.625 and second column is 0.5 and 1.5. So, again after simplification the value of p 0 1 2 3 is equal to 29.95. So, after this calculation the final table is this one. In this table the last column is updated. So, the value of y when x equal to 1.5 is the last value, that means the 29.95. This is the final value of y when x equal to 1.5. So, this is the Aitken interpolation method to find the value of y for a given x, and note that the argument is not necessarily equispaced. This is the one advantage of Aitken interpolation method. The argument may or may not be equispaced. Now, we consider another problem to illustrate Aitken formula. In this formula, we have to determine a quadratic polynomial from the following table of values. So, in this table there are 3 values are given. So, for this table we can calculate or we can generate only one quadratic polynomial. In the first approximation, the formula is p 0 j equal to 1 by x j minus x 0, in first column y 0 y j, second column x 0 minus x, x j minus x, and this is true for j equal to 1 and 2. Now, for j equal to 1, the value of p 0 1 equal to 1 by 1. 1 by 1 means x 1 minus x 0 is 1, first column is 7 5, this is the values of y 0 and y 1, and second column is 1 minus x and 2 minus x, because the value of x is not given here. So, after simplification the value of p 0 1 is equal to 9 minus 2 x. So, this is a polynomial of degree 1. Similarly, for j equal to 2, the value of p 0 2 equal to 1 by half into a determinant whose first column is 7 2 and second column is 1 minus x and 3 minus x. So, after simplification this polynomial becomes half into 19 minus 2 x. Note that this is also a linear polynomial. The second approximation is p 0 1 j equal to 1 minus x j minus x 1 into a determinant whose first column is p 0 1 and p 0 j, second column is x 1 minus x and x j minus x for j equal to 2. And for j equal to 2, the value of the polynomial p 0 1 2 equal to 1 by 1, because x j minus x 1, that means x 2 minus x 1 is 1, and the value of p 0 1 and p 0 2 are obtained in the first approximation, that values are 9 minus 2 x and half 19 minus 5 x, and second column is 2 minus x and 3 minus x. So, after simplification this determinant gives 8 minus half into x minus half into x square. So, this is the quadratic approximation of the given table of values. And finally, the required quadratic polynomial obtained by Aitken formula is 8 minus 0.5 into x minus 0.5 into x square. So, this is the final answer for this table of values or for this problem. So, now we shall discuss about another important interpolation method called the Hermite interpolation, and in this method we shall consider 3 sets of values, one for x, other for y, and third set is the derivative of y. So, the other interpolation method generally uses 2 sets of values x and y, but here we shall use additional n plus 1 values, that one are the first derivative of y. So, n plus 1 additional values are available for this problem. Therefore, we can construct a polynomial whose degree is 2n plus 1 instead of degree n, which are used in other interpolation method. So, in this method we consider n plus 1 arguments x 0, x 1 up to x n, and n plus 1 values of y, that means the value of f of x I for I equal to 0 to n, and the another set of values, that one is the first derivative of f at x I equal to 0 to n. So, we have additional 2 plus 2n number of values. So, for this additional number of values we can construct a polynomial of degree at most 2n plus 1. Now, let the Hermite interpolating polynomial be the following form: phi x equal to summation I equal to 0 to n h I x f of x I plus summation I equal to 0 to n capital H x and first derivative of x I. So, h I x and capital H I x for all I equal to 0 to n are the polynomials in x of degree at most 2n plus 1. So, finally, phi x is a polynomial of degree at most 2n plus 1, but by the condition of interpolating polynomial we obtain small h I x j equal to 1 for equal I and j, and it is 0 for different I and j, and the condition for capital H I at x j equal to 0, and this is one true for all I. Similarly, for small h I, the first derivative of small h I at x j equal to 0 for all I. Capital H I dash at x j means the first derivative of h I at x j equal to 1 for the same I and j, and 0 for different I and j. So, these conditions are similar to the conditions which are applied for Lagrangian function. The Lagrangian function Lix is defined by Lix equal to x minus x 0 up to x minus x n except the factor x minus x I whole divided by x I minus x 0 to x I minus x n except the factor x I minus x I, and this is true for I equal to 0 to n. Obviously, Lix j equal to 1 for same I and j and equal to 0 for different I and j. So, this condition, the condition for Lagrangian function, is similar to the condition which are imposed in equation 7 and 8 for Hermite interpolating polynomial. So, we can express h I x and capital H I x in terms of Lagrangian functions, and they are considered as small h I x equal to a I x plus b I whole into L I x whole square, and capital H I x equal to C I x plus d I whole into L I x whole square. Note that a I x plus b I is a linear polynomial and L I x is a polynomial of degree n. So, L I square is a polynomial of degree twice n. That means, small h I x is a polynomial of degree 2n plus 1. Similarly, capital H I is a polynomial of degree 2n plus 1. Now, we determine the value of a I, b I, c I, d I. To determine this value, we consider the conditions 7 and 8 which are essential for interpolating polynomial, and using these conditions we obtain these 4 equations: a I x I plus b I equal to 1, c I x I plus d I equal to 0, a I plus 2 first derivative of L I at x I equal to 0, and c I equal to 1. Now, from the third equation we get a I equal to minus 2 into first derivative of L I at x I, and from the first equation we obtain b I equal to 1 plus 2 x I into a I. The value of a I is obtained, that one is minus 2 first derivative of L I at x I, that means b I equal to 1 plus 2 x I into first derivative of L I at x I, and from the fourth equation we get c I equal to 1, and hence from the second equation you obtain the value of d I, that one is equal to minus x I. Now, we using these values a I, b I, c I, d I, we get the value of h I x and capital H I x as follows: small h I x equal to minus 2 x into first derivative of L I at x I plus 1 plus 2 x I into first derivative of L I at x I whole into L I x square. After simplification, this expression reduces to 1 minus 2 into x minus x I into first derivative of L I at x I whole into L I square, and capital H I x equal to x minus x I into L I x whole square. So, we obtain the value of small h I and capital H I in terms of Lagrangian functions. Thus, the Hermite interpolating polynomial is phi x equal to summation I equal to 0 to n of 1 minus 2 into x minus xi into first derivative of Li at xi whole into Li x square into f of xi plus summation I equal to 0 to n x minus xi Li x whole square into first derivative of f at xi. So, this is the Hermite interpolating formula or polynomial, and this formula is applicable for unequal and equal space arguments. Now, we illustrate the Hermite interpolating methods by considering an example. In this problem, we have to determine a fifth degree polynomials, Hermite interpolating polynomials, which satisfies the following table of data, and from this polynomial we have to calculate the approximate value of y when x equal to 1.5. Note that here three sets of values are given, x equal to 1, 2, 3, and the corresponding value of y are 1, 8 and 27, and the derivative of y at this point are 3, 12 and 27. So, for these three sets of values we can construct a polynomial of degree 5. Since all small hi and capital Hi which are appears in the Hermite interpolating polynomials, all this h depends on Lagrangian function. So, for this case we have three Lagrangian function L0x, L1x and L2x. Now, L0x equal to x minus x1 into x minus x2 whole divided by x0 minus x1 into x0 minus x2. By using the values of x0, x1 and x2, we get the value of L0x which is equal to half into x square minus 5x plus 6. Similarly, we obtain the value of L1x for using the values of x0, x1 and x2, and that one is minus of x square minus 4x plus 3, and the value of L2x is similarly obtained by this formula, and it is equal to half into x square minus 3x plus 2. Once the values of L0, L1 and L2 are available, then we can calculate their derivatives which are required in small hi and capital Hi. Now, the first derivative of L0 at x which is equal to half into 2x minus 5, and first derivative of L1 at x is equal to minus of 2x minus 4, and first derivative of L2 at x equal to half into 2x minus 3. Thus, the values of first derivative of L0 at x0, this value is required, and this is equal to minus 3 by 2, and the first derivative of L1 at x1 equal to 0, and first derivative of L2 at x2 equal to 3 by 2. Now, we can determine all the values of small h and capital H. Now, small h0x equal to 1 minus 2 into x minus x0 into first derivative of L0 at x0 whole into L0x power 2. So, using the values of L0 dash x0 and L0x, we obtain the values of small h0x equal to 14 into 3x minus 2 into x square minus 5x plus 6 whole to the power 2. Similarly, the value of h1x is equal to x square minus 4x plus 3 power 2, because in this case the first derivative of L1 at x1 is 0, and the h2x equal to we get 1 by 4 10 minus 3x into x square minus 3x plus 2 whole square. Similarly, the capital H0x equal to x minus x0 L0x whole square, and this is equal to 1 by 4 x minus 1 into x square minus 5x plus 6 whole to the power 2, and h1x equal to x minus x1 into L1x whole square, which is equal to x minus 2 into x square minus 4x plus 3 whole square using the values of x1 and L1x, and similarly we get the value of h2x equal to x minus x2 L2x whole square, and this is equal to 1 by 4 x minus 3 into x square minus 3x plus 2 whole square. So, using all these values of small h and capital H, we get the Hermite interpolating polynomial as phi x equal to 1 by 4 3x minus 2 into x square minus 5x plus 6 whole square into 1, that one is the value of f at x 0, plus x square minus 4x plus 3 whole square into 8, this is the value of f at x 1, plus 1 by 4 10 minus 3x into x square minus 3x minus 2 whole square into 27, this is the value of f at x 2, plus 1 by 4 x minus 1 x square minus 5x plus 6 whole square into 3, this is the value of f dash at x 0, plus x minus 2 x square minus 4x plus 3 whole square into 12, 12 is the value of f dash at x 1, plus 1 by 4 x minus 3 x square minus 3x plus 2 whole square into 27, 27 is the value of first derivative of f at x 2. After slight modification, this expression becomes, or this polynomial becomes 1 by 4 6x minus 5 into x square minus 5x plus 6 whole square plus 12x minus 16 into x square minus 4x plus 3 whole square plus 27 by 4 into 7 minus 2x into x square minus 3x plus 2 whole square. So, this is the partial simplification, and note that each term is a polynomial of degree 5, and it is obvious as per the theory of Hermite interpolating polynomial, and this polynomial contains 3 terms, each term is of degree 5. So, after final simplification we get a polynomial of degree 5. Now, the second part of the problem is to find the value of y when x equal to 1.5. So, we have substituted the value of x equal to 1.5 to this polynomial, and after simplification we get the value of y at x equal to 1.5 which is equal to 3.375, and this is correct up to 3 decimal places or 4 significant figures. So, in this module we have discussed 2 interpolating methods. One is Aitken interpolating method, that one based on iteration, and other is Hermite interpolation method. In Hermite interpolation method we consider 3 sets of values, one is for x, other is for y, and other is for the derivative of y, and this is unusual compared to the other interpolating methods. But these 2 methods are applicable for all types of arguments, that means for unequal arguments as well as for equal space arguments.